Hello and welcome to Into the Abyss podcast. My name is Todd Decker. Where do the laws of physics come from? This question is the subtitle of Victor Stenger's 2006 book, Comprehensible Cosmos. I think this question is one version of the more general guiding question of my whole intellectual life. Why are things the way they are? Stenger has a very interesting response to this question, which is based on what he calls the principle of point of view invariance. The models of physics cannot depend on any particular point of view. The path from this principle to the laws of physics goes through an important theorem known as Noether's theorem. This theorem was developed by Emmy Noether in 1918. Put briefly, the theorem says that symmetries in a system generate conserved quantities. Anyone who studied and remembers physics will know of the conservation of momentum, conservation of angular momentum, and the conservation of energy. These conservation laws are absolutely foundational, and what's remarkable is that there's a reason for them. These conservation laws come from symmetries. The conservation of momentum, angular momentum, and energy come from symmetries of translation, rotation, and time. Stenger puts it this way, quote, "In any space-time model possessing time translation invariance, energy must be conserved. In any space-time model possessing space translation invariance, linear momentum must be conserved. In any space-time model possessing space rotation invariance, angular momentum must be conserved." Thus, the conservation principles follow from point of view invariance. If you wish to build a model using space and time as a framework, and you formulate the model so as to be space-time symmetric, then the model will automatically contain what are usually regarded as the three most important laws of physics, the three conservation principles. Close quote. To me, this is quite remarkable, but maybe I'm just easily impressed. So I went online to see how others view all this. I looked up on Quora responses to the question, what is the significance of Noether's theorem? Here are some responses. Quote, "I think it is almost the thing that makes sense of physics. Physics is based on a large number of conservation rules, conservation of energy, momentum, etc. Without Noether's theorem, all you can say is that they are conserved. They are just givens. With the theorem, you can say that they arise from symmetries of the space we live in. In a space which did not have these symmetries, these conservations would be so different from the space we know as to be unrecognizable. It derives the otherwise arbitrary conservation rules from intuitively understood symmetries. Brilliant." Close quote. Quote, "Most of the fundamental physics could be interpreted as positing a symmetry, then handing that symmetry off to Miss Noether and asking her to tell us what the resulting physics is. In other words, without Noether's theorem, there wouldn't be most of modern physics." Close quote. And my favorite, quote, "It's a matter of life and death. Being a physics student, the Noether's theorem is extremely important with everything I do. If it were falsified, the whole structure of modern physics would crumble." Close quote. So it's a pretty big deal. Hopefully that sparks some interest. Now let's dig into it and see how it works. Invariance and transformations. First, let's revisit this idea of point of view invariance. One of the first things you do in a physics problem is define your coordinates. If you're on the surface of the Earth, you usually set one axis pointing up away from the center of the Earth. This is what we're used to thinking of as up. That's because in our everyday experience, there pragmatically is an obvious coordinate system to use. That's an up and a down. But that's because we reference our everyday experience relative to Earth, which we're living on. But we know, at least since the Copernican revolution, that this coordinate system isn't absolute. The Earth isn't the center of the universe, even if it is the center of our lived experience. But it's not just that. There is no center of the universe at all. There's no absolute up or down. That doesn't mean that we don't use coordinates. Of course we do. We have to. But it does mean that the coordinate system we use is not absolute. We usually use one that makes things easy for our calculations. But the system we represent in one coordinate system can also be represented in a different coordinate system. This is easy to see with vectors. Let's represent a vector on an xy Cartesian coordinate system. The vector will start from the origin, 0, 0, and go out to point 4, 3. What's the magnitude of this vector? We calculate that by the equation the square root of x2 minus x1 squared plus y2 minus y1 squared. And plugging in our values, square root of 4 minus 0 squared plus 3 minus 0 squared is equal to the square root of 4 squared plus 3 squared is equal to the square root of 16 plus 9 is equal to square root of 25, which is equal to 5. The magnitude of this vector is 5. Now let's change the coordinate system by shifting it 2 to the right and 7 up. Now this same vector starts at -2, -7, and goes out to 2, -4. What's the magnitude? Square root of -2 minus 2 squared plus -7 minus -4 squared is equal to the square root of -4 squared plus 3 squared is equal to the square root of 16 plus 9 is equal to the square root of 25, which is equal to 5. The magnitude is still 5. Now let's go back to the first coordinate system and rotate it 30 degrees counterclockwise. 30 degrees in radians is pi over 6 radians. We make this transformation using the rotation matrix r equals cosine theta, negative sine theta, cosine theta. And we multiply r by our vector x, y. The result is rv equals x cosine theta minus y sine theta, x sine theta plus y cosine theta. And this equals rv equals 3/2 times square root of 3 minus 2, 3/2 times 2 times square root of 3. And this is approximately equal to rv equals 0.598, 4.964. For our transformation, theta is pi over 6 radians. Our new vector coordinates are 0, 0, and approximately 0.598, 4.964. Now the moment of truth. After all that, what is the magnitude? It's square root of 0.598 minus 0 squared plus 4.964 minus 0 squared is equal to square root of 0.598 squared plus 4.964 squared equal to square root of 0.358 plus 24.642, which is equal to square root of 25, which is equal to 5. The magnitude is still 5. When we look at this visually, it's actually not surprising. The vector stays the same in all these cases. It's just the coordinate system that's moving around. This is the basic idea of invariance. And I think it gives a general sense about how something can remain constant if it doesn't depend on these coordinate system transformations. The Lagrangian. Before getting to Noether's theorem itself, we need to talk about the Lagrangian, because Noether's theorem is expressed in terms of it. The Lagrangian is a function that describes the state of a system and is equal to the difference between the total kinetic energy T and the total potential energy V of a system. L equals T minus V. The Lagrangian is used in Lagrangian mechanics and is a different way of looking at systems than Newtonian mechanics. Instead of looking at forces as in Newtonian mechanics, in Lagrangian mechanics we're looking at energies. The Lagrangian is a function of spatial coordinates and their derivatives with respect to time. Spatial coordinates could be the familiar Cartesian xyz coordinates, but it's customary to generalize these with a single variable, for example, q. For multiple spatial coordinates, we can just number them off. Q equals q1, q2, out to qn. The time derivative of q is q dot. The time derivative of a spatial coordinate is velocity. So some of the familiar quantities of Newtonian mechanics will be expressed differently in Lagrangian mechanics. Most notably, momentum. In Newtonian mechanics, we express momentum as mass times velocity, P equals mv. To express this in terms of a Lagrangian, let's change v to q dot, so P equals mq dot. Now, the Lagrangian is the difference between kinetic energy and potential energy, L equals T minus V. Kinetic energy is T equals 1/2 mv squared, or T equals 1/2 mq dot squared. So we can rewrite the Lagrangian as L equals 1/2 mq dot squared minus V. Now, taking the derivative with respect to q dot, delta L delta q dot equals mq dot, and mq dot equals P, so P equals delta L delta q dot. And that's the equation for momentum in terms of the Lagrangian, P equals delta L delta q dot. So momentum is the derivative of the Lagrangian with respect to velocity, also the derivative of kinetic energy with respect to velocity. The Hamiltonian. There's another function I want to go over before moving on to Noether, and that's the Hamiltonian function. The Hamiltonian is similar to the Lagrangian, except that it's the sum of kinetic energy and potential energy, instead of the difference between them. H equals T plus V. The Hamiltonian is the total energy of the system, and we can express this in terms of the Lagrangian. Since L equals T minus V, we can express the potential energy as V equals T minus L. Substituting this into the Hamiltonian, H equals T plus V, h equals t plus t minus L, h equals 2t minus L, h equals 2 times 1/2 times mq dot squared minus L, h equals mq dot minus L. Since p equals mq dot, h equals p q dot minus L. And since also p equals delta L delta q dot, h equals delta L delta q dot times q dot minus L. This is the expression for the total energy in terms of the Lagrangian. H equals delta L delta q dot times q dot minus L. The Lagrange-Euler equation of motion. One more equation we should introduce before getting into Noether's theorem is the Lagrange-Euler equation, also called the equation of motion. This has the form d dt delta L delta q dot equals delta L delta q. What is this equation saying? Let's translate this out of the Lagrangian form into the more familiar Newtonian quantities. An equivalent form of this equation is dp dt equals negative delta v delta q equals f, or dmv ddt equals f, or ma equals f. This is Newton's second law. It's just expressed in a different form with the Lagrangian, which again is d dt delta L delta q dot equals delta L delta q. We'll be plugging this equation into a lot of things in the foregoing, so it's important. Noether's theorem. Now let's move to Noether's theorem. We'll look at Noether's theorem for the conservation of momentum, the conservation of angular momentum, and for the conservation of energy. We start with the Lagrangian as a function of position q and velocity q dot. L of q, q dot. What we're going to do is apply the following transformation on q and q dot. Q goes to q of s, q dot goes to q dot of s. If our Lagrangian has symmetry, it should not change under this transformation to s. Expressed mathematically, this means dds of L q of s q dot of s equals 0. Let's propose that under this transformation that there is a conserved quantity c of the following form. C equals delta L delta q dot times delta q delta s. And since it is a conserved quantity, it does not change over time. That is, dc dt equals 0. And here's the proof for that. Take the proposed quantity c and take the time derivative of it. C equals delta L delta q dot times delta q delta s. dc dt equals ddt of delta L delta q dot times delta q delta s. Since we have two variables, q and q dot, we need to apply the product rule. dc dt equals ddt of delta L delta q dot times delta q delta s plus delta L delta q dot times delta q dot delta s. Now recall the Euler-Lagrange equation of motion. ddt of delta L delta q dot equals delta L delta q. We're going to plug that in here to get dc dt equals delta L delta q times delta q delta s plus delta L delta q dot times delta q dot delta s. What do we have here? The right-hand side of this equation is what we get when we apply the chain rule to the derivative of the Lagrangian with respect to s. dds of L q of s q dot of s equals delta L delta q times delta q delta s plus delta L delta q dot times delta q dot delta s. And this is equal to 0. So dc dt equals delta L delta q times delta q delta s plus delta L delta q dot times delta q dot delta s, which is equal to dds of L of q of s q dot of s, which is equal to 0. And dc dt equals 0. So what's been proved here is that if the Lagrangian L does not change with respect to transformation S, then the conserved quantity C doesn't either. That's Noether's theorem. Now let's look at some applications, examples of conserved quantities that result from different symmetries. Conservation of linear momentum. To get the conservation of linear momentum, we're going to say that the Lagrangian is symmetric under continuous translations in space. Our spatial coordinates are q equals q1, q2, out to qn. And we'll apply the transformation q to q of s, where q of s is equal to q plus s. So we're just sliding our coordinate system over by an interval s. The conserved quantity c is c equals delta L delta Q dot times delta Q delta S. Taking the derivative of q with respect to s, delta Q delta S is equal to delta delta S of q plus s, and that's equal to 1. So c becomes c equals delta L delta Q dot equals p, which is momentum. So when we apply the spatial transformation q to q of s, the conserved quantity c is momentum p. In other words, the conservation of momentum results from symmetry in space. To give some interpretation, this means that the system has no dependence on where it is in space. It's not being acted upon by any external forces. If there were an external force, then it would depend on its location in space. Recall that force is equal to F equals ma, F equals m dv dt, F equals d dt mv, F equals dp dt. Force is equal to the rate of change in momentum with respect to time. So clearly, if there is a non-zero external force acting on the system, momentum is not constant. If there is an applied force external to the system, like with a spring, then momentum is obviously not conserved. And with such forces, location makes a difference. With a spring, it matters how much the spring is stretched, so momentum is not conserved in such cases where there's not symmetry in space for that system. But in systems that do have symmetry in space, momentum is conserved. Conservation of angular momentum. To get the conservation of angular momentum, we're going to say that the Lagrangian is symmetric under continuous rotations in space. We apply the transformation q to q of s, in which case s is some angle of rotation. This is a two-dimensional case where q is represented by the matrix q1, q2. We make this transformation using the rotation matrix r equals cosine s, negative sine s cosine s, and multiply r by our matrix q1, q2. The result is rq equals cosine s, negative sine s cosine s, times q1, q2. For very small values of s near 0, sine s is about equal to s, and cosine s is about equal to 1. This makes the rotation matrix equal to 1, negative s, 1. So the transformation is 1, negative s, 1, times q1, q2. The result of this transformation is that q1 goes to q1 minus s times q2, and q2 goes to q2 plus s times q1. For reasons that will be clear shortly, let's differentiate these. dq1 ds is equal to negative q2. dq2 ds is equal to q1. Now let's bring in our conserved quantity c. c equals delta L delta Q dot times delta Q delta S. And since q equals q1 q2, c equals delta L delta Q dot 1 times delta Q1 delta S plus delta L delta Q dot 2 times delta Q dot 2 delta S. Or in terms of momentum p, c equals p1 times delta Q1 delta S plus p2 times delta Q2 delta S. The derivatives in this equation are equal to the derivatives we just calculated for Q1 of S and Q2 of S. So, plugging those in, c equals Q1 times P2 minus Q2 times P1. And this is equal to the cross product c equals Q cross P, which is angular momentum L. Angular momentum is equal to the cross product of linear momentum and the position vector. So, c equals L. The conserved quantity c is angular momentum. In other words, angular momentum results from symmetry of rotation. To give some interpretation again, this is the condition in which the system has no external rotational forces, i.e. torque. To use the example of a spring again, if this were a system where we're winding up a torsion spring, then angular momentum very much matters. The tighter we wind it up, the higher the torque. In that kind of system, angular momentum is not conserved. But in the absence of that kind of torque, angular position and rotation don't matter. So angular momentum is conserved. Conservation of energy. To get the conservation of energy, we're going to say that the Lagrangian is symmetric in time. So we have our Lagrangian, L of q dot, And we're going to say that it doesn't change with time. dl dt equals 0. Let's see what follows from this. First, let's go to the derivative of the Lagrangian with respect to time. To do this, we apply the chain rule. dl dt equals delta L dq times delta q dt plus delta L dq delta q dot times delta q dot delta t plus delta L delta t. We already set delta L dt to 0, so that goes away. And let's simplify delta q delta t to q dot and delta q dot delta t to q double dot. dl dt equals delta L delta q times q dot plus delta L delta q dot times q double dot. Recall from the Euler-Lagrange equation that delta L delta q equals ddt of delta L delta q dot. And we plug this in to get dl dt equals ddt of delta L delta q dot times q dot plus delta L delta q dot times q double dot. This is actually a result of the following application of the product rule. ddt of q dot times delta L delta q dot equals ddt of delta L delta q dot times q dot plus delta L delta q dot times q double dot. So we can plug that in to get this more compact result. dl dt equals ddt of q dot times delta L delta q dot. Rearranging this, we get 0 equals ddt of q dot times delta L delta q dot minus L. Maybe this looks familiar. Recall that the Hamiltonian, which is equal to the sum of kinetic and potential energy, has the following form, expressed in terms of the Lagrangian. H equals delta L delta q dot times q dot minus L. So we can plug this into our equation to get ddt of H equals 0. Let's go ahead and express this in terms of kinetic energy T and potential energy V. H equals T plus V. ddt of T plus V equals 0. So from our starting condition, dl dt equals 0, we get ddt of T plus V equals 0. If we set the condition where the Lagrangian doesn't change with time, then the total energy is conserved. This is the Noether symmetry conservation relation. What would it be like if things weren't this way? Under time symmetry, things like the gravitational constant and the masses of fundamental particles are constant across time. But what if they weren't? An object elevated above the Earth's surface has potential energy V equals m lowercase g h, where m is mass, lowercase g is acceleration due to gravity, and h is height. Acceleration due to gravity is a function of the gravitational constant uppercase g. Lowercase g equals negative uppercase g times uppercase m divided by r squared, where uppercase m is the mass of the gravitational field source, like the Earth, and r is the distance from the center of the Earth. For the elevated object in our example, none of these values is changing. But what if we could change the gravitational constant uppercase g? Say we increase it. Now acceleration due to gravity lowercase g is higher and potential energy v is higher. We've created energy from nowhere. Or another example, at one moment in time you throw a ball up into the air with a certain velocity. So it starts off with a kinetic energy that gets converted to potential energy as it goes up into the sky. But then, right as it reaches its highest point, you turn the gravitational constant, uppercase g, way up, and the ball slams to the ground at a much faster velocity than you started with. Again, we've created energy from nowhere. But that doesn't happen because the laws of physics don't change over time. Philosophical reflections. If you were to create a universe, how would you do it? I don't know how to create a universe, but if I did, my inclination would be to make it as self-designing as possible. Set a few basic rules and let things develop from there. This seems to be the most efficient and elegant way to configure things. I think what makes Noether's theorem so marvelous is that we get a great deal of purchase from a rather simple principle, symmetry. This reminds me a little of what Immanuel Kant tried to do in his moral philosophy. In his 1785 Groundwork of the Metaphysics of Morals, he proposed that all moral principles could be derived from one master principle called the Categorical Imperative, which was the following, quote, act only according to the maxim whereby you can, at the same time, will that it should become a universal law, close quote. This is also known as the Principle of Universalizability. This reminds me of Noether's theorem in two ways. First, it's a simple principle from which others can be derived. Second, it's a principle of universalizability. We could say that Kant is making his ethics point of view invariant. I should act only according to a maxim that could be a universal law, that is not only applicable to me, but to anyone. That's what it means for it to be universalizable. In Comprehensible Cosmos, Victor Stenger also proposes a principle of universalizability, but for physics. Quote, "The models of physics cannot depend on any particular point of view." Close quote. That's the principle of point of view invariance. Stenger says of this principle, quote, "Physics is formulated in such a way to assure, as best as possible, that it not depend on any particular point of view or reference frame. This helps makes possible, but does not guarantee, that physical models faithfully describe an objective reality, whatever that may be. When we insist that our models be the same for all points of view, then the most important laws of physics as we know them appear naturally. The great conservation principles of energy and momentum, linear and angular, are required in any model that is based on space and time, formulated to be independent of the specific coordinate system used to represent a given set of data. Other conservation principles arise when we introduce additional, more abstract dimensions. The dynamical forces that act for the interactions between bodies will be seen as theoretical constructs introduced into the theory to preserve that theory's independence of point of view." Close quote. Sort of like Kant's principle of universalizability, point of view invariance keeps us honest. Repeatability of experiments by multiple observers, holding constant only those factors relevant to the experiment, is what ought to finally convince others of the validity of our observations. It won't do much good if I have a singular experience that only I observe, that, in other words, is not universalizable, not point of view invariant, but rather strictly tied to me and my point of view. That's not to say that we don't have private subjective experiences that are real. They're just phenomena of a different nature. Here's more from Stenger on this point. Quote, "So where does point of view invariance come from? It comes simply from the apparent existence of an objective reality, independent of its detailed structure. Indeed, the success of point of view invariance can be said to provide evidence for the existence of an objective reality. Our dreams are not point of view invariant. If the universe were all in our heads, our models would not be point of view invariant. Point of view invariance generally is used to predict what an observer in a second reference frame will measure given the measurements made in the first reference frame." Close quote. I think that's well put, and that line that our dreams are not point of view invariant is one I think about a lot. Noether's theorem is absolutely foundational. It's been said that Noether's theorem is second only to the Pythagorean theorem in its importance for modern physics. It's remarkable that just one compact principle can produce so much of what we observe in the world.